Welcome back, Matt. How was your trip?
Pretty good.
Good. All right, do me a favor, make sure you have a calculator for today. We're going to be using it for some calculations. I know. Well, these days you can use a calculator to just look at a graph, too.
But that's calculating the graph. It's still direct calculation. What?
All right, so last week we were introducing our concept of a logarithm, and we were looking at how we can have different bases of a log. We can have a base of 3, we can have a base of 7. I think I discussed how computers have a base 2 language. What's our base system? 10, okay, aka a common log, where we don't really write the number 10 at the bottom or in that little subscript, so if we don't see it, we understand that it's a 10. What we're going to take a look at today is kind of a different type of log. It's still a log in itself, but the base is something very special. So just like a common log has a base of 10, that's special for us because that's our counting system, our number system. We're going to take a look at what's called the natural base of E. Maybe you've heard of this before, maybe you haven't, but we're going to take a look at what this letter E represents, meaning what number it actually means. So do me a favor, on your calculator, take a second or two to plug these n values into this exponential function, and I want you to see what numbers you get out. Maybe go to 3 decimal places when you start to get some of these values.
That wasn't me, that's not the handwriting.
It does. Look.
Let's go to 2.7.
No, I do not like that.
1, 9, 6, 2 are repeating numbers. 2.7182818. Boy, I did all of them. I know, but then if you type in just like another all, it gets to alright. We're gonna do 1, 2,
Tyson put it.
You know how he is.
number 3.
I don't know a lot on my locker effects, but
Don't spoil anything, because I've never watched anything on it, never even. Literally, the most I've heard was it's a hard game. I was bored, I was like, I don't get the game, why not? So far to the point where, I'm in like the second area, but I'm progressing slowly. I'm not like just doing all the one things, I'm doing all the side quests too. Because I like that, that's more enjoyable to do.
Did you guys start to notice a pattern after a while?
I did 15 zeros.
2.718, 2.718, 2.718. What if we were to do 100 million? Think you'd get the same? I'd probably agree. Okay, so if we were to continue making our n values get very, very large, we could probably assume that our output or y value is going to be around 2.718. Okay, what this special value is referred to is letter E, which is called the natural base. Now, the letter E is something special, just like the number pi. Do we know what pi is as a decimal? 3.141592.6. Oh, look at us go.
5, 3.
Maybe you could keep going.
No, 5, 3, 5.
Okay. On your calculator, the pi button is in blue, underneath clear. So if you were to hit second caret, it'll bring up the pi button, and you can hit enter, and there's pi to so many decimals. Notice how the letter E is in blue right underneath it. You'd have to hit second divide. And if you hit that, you'll get 2.718281828, and so forth. Okay? So this letter E, it's not a Greek letter like pi is, but the letter E actually stands for the person who discovered this number, 2.718. Say it again. Euler. Right. Okay. So Euler was a Swiss mathematician who was dealing a lot with horizontal asymptotes, by the way, which this 2.718 is for this exponential function. Notice how as the x, in this case n values, get really large, meaning as you go to the right of this graph, you're approaching 2.718. You're leveling off. So the reason that this particular number is really special, why it's called the natural base, is because this number is used a lot in nature, like in our Earth system. Okay, you might see it a lot in biology. Just like how pi is used a lot with circles, like circumference and area, this letter E is used a lot in our natural Earth system. So that's why it's called the natural base. Okay, it shows up a lot in our natural world. So what I want us to try to do is write a natural exponential equation and see if we can convert that to a natural log equation like we were doing last week. If you flip the page for a moment and look at all those 15 examples, we were converting between logs and exponentials. And maybe we can do a little bit of that today. So this base, this natural base of E, if I want to use it as an exponential, the E is going to be my base, and I'm going to have to raise it to some power. Maybe I'll just keep it simple and raise it to a power of 2. So on our calculator, we're going to take this letter E. Now you can do the second divide button to bring up that letter E like we did before, or notice how kind of next to the number 4, do you see how it says e to an x? You could select that option, and it's going to bring up a little box for you to write in a power. Okay, so e squared is 7.389. Okay, if we were to square 2.718, we'd get 7.389. Okay, so this is a natural exponential. Natural meaning it's a base of e, this 2.718. If we were to convert this to a logarithm, like we did last week, if we have a base of e in the exponential, that would have to be our little base that we use for the log. Okay, so log with a little base of e. If logs are powers, then this logarithmic equation should equal this power of 2, and this 7.389 number is going to be the argument. Okay, we did a little bit of that on Thursday when we were converting between logs and exponentials. So this is what it would look like based off of our knowledge from Thursday last week, but again, since this base of e is special, we don't really write log base e. Are you familiar with perhaps how it's rewritten? What it looks a little differently? Yeah. ln. Okay, so instead of log with a base of e, we use an ln symbol or notation that means natural log. I know it says ln, and you would think natural log would go NL, but since, you know how in some foreign languages they kind of flip the order of the adjective or how the descriptor, okay, it's kind of flipped here as well. So this is actually logarithmic natural, okay, if you want, I know, so this is natural log, just in a descriptive or different language based the way it's written. So instead of log base e, we're going to use natural log ln. The argument is still 7.389, and it's still going to equal 2. Okay, so whenever you see the base of e, I want you to understand natural exponential or natural log, depending on the context that we're using it in. Okay, do you think we can do that? Yes? Okay, 2.718, let it sink in. Okay, 2.718, just like pi is 3.14. Let it sink in, 2.718. So, I wanted to take a second and just review some of the ways that we can use our calculator to help us solve or simplify these logarithmic equations. I don't think it's going to be necessary for us to do all three of them because we did a lot last week, but maybe we'll just do the first one. Okay? Can we think about in our heads a number that we'd have to raise the base of 3 to get 20? If we can't figure it out exactly in our heads, can we sandwich it? Can we guess between two numbers? Yeah? 2 and 3? Why 2 and 3? 9 and 27. Okay, so the base of 3 squared would be 9. The base of 3 cubed would be 27. 20 is in between those numbers. So the value of this log, aka the power we would need, is something between 2 and 3. Can we revisit how we can type this in on our calculator? Okay. You can hit the math button, and then it's option A, okay? If your calculator has this capability, go ahead and use it. So math, scroll down to letter A. Okay, not every calculator has this ability. We have to be clear on that. So we'll type in 3 as the base, and then 20 for the argument. We'll get 2.727. All right. How would you have to find the same value, 2.727, if your calculator did not have that capability? Bless you. I know this one's probably the preferred one, okay, but what if you had one of those slim calculators that you guys use like in middle school? Because that doesn't have this capability. How would you have to use that instead? Got it, Erica? There we go. We're going to use this common log button next to number 7. Okay, base of 10. So we would need common log of the argument, which is 20, over the common log of the base, which is 3. And we'll get 2.727. What's interesting is that instead of using a common log, you could use this natural log. Okay, notice how on the left-hand side, right underneath the common log button is the natural log, that ln. You could type in natural log of 20 over natural log of 3. And you'll get the same thing, 2.727. Okay, so we have 3 different methods that we can use on our calculator to help us find the value of a log. The last 2, I'll go ahead and star them, are the ones that absolutely any calculator can do. Okay, you can do them on your phone. This math A is the one that's kind of special. Okay, if your calculator has it, then you can use it. But realize if it doesn't, you should be familiar with at least these other two methods. Is that clear? We have 3 methods, 2 of which will work every time. Okay? So, now that we have this understanding of what a natural log is, that base of e, we can convert between logarithmics and exponentials. Let's go ahead and try to solve some very simple, very basic log equations. Throughout the unit, they're going to start to get a little bit more involved, and we're going to practice them, and we'll talk about them. But I think we have enough knowledge, at least at this point, to solve basic ones. Okay, so let's see how these go. Notice how, for our first one, log base 9 of x equals -2/3. We're going to try to figure out what the argument of this log would have to be in order for the power, aka answer, to be -2/3. Can we convert this logarithmic equation into an exponential? Can we rewrite it perhaps to help us? Can we think about where each one of those numbers or variable would be written in an exponential function? Maybe look, flip the page from what we did on Tuesday, and you had those 15 examples that we converted. Maybe that would help. All right, take a look at these 15 from Thursday. Can we make a connection to this example? Can we convert it? Let's pick it apart. What's the base of this log? 9, okay, so we'll start there. If the 9 is a base for a log, then that's going to be the same base for your exponential. If this is a base, that means the 9 has to have some type of power on it. Can we think about between the x and the -2/3, which one would be the power? Go, Blair? Good, okay, logs are powers. So this log, aka power, is -2/3. And that means the argument of x is going to be the answer or the output for this exponential function. So we just converted a log equation to an exponential. Let's see if we can rewrite it a little bit to help us solve for x. So this is probably going to involve some properties of exponents that we were familiar with or reviewed from the last unit. Can we rewrite this in any way? The first thing I notice is a negative power. Can we get rid of that negative power? I heard flip it. Okay, so this would be 1 over 9 to the 2/3. Can we rewrite that power of 2/3? Can we think about how to solve that? Yeah? Okay, so we could do the cube root of 9 squared, and then 9 squared would be 81. Okay, so the bottom or the denominator of 3 symbolizes the root. The numerator of 2 signifies the power on the base inside that root. Bless you. All right, so there's our solution for x. Maybe we'll check it since we have a calculator. I'm going to go ahead and plug in this 1 over cubed root of 81 in for that x, and hopefully my calculator gives me a negative 2/3 as my answer. So I'm going to use the log base ability just because my calculator has it. So my base is 9, and for my argument, I'm going to type in 1 divided by the cube root of 81. To get your cube root button, you have to hit the math button again, and it's option 4. You see that little 3 with a check mark. So inside that, I'll type in 81. And if I hit enter, I get a negative 2/3. All right, so I checked my work. It looks like I converted appropriately, I rewrote appropriately, I solved it appropriately, because if I plug it back in, I get the solution that the equation is telling me I should have. Okay, so checking my work, always a good thing. Are we good to go? We try another one? Ladies in the back, are we okay? We sure? It sounds hesitant. You'll figure it out? Let me know if you don't, okay? Okay. All right, let's go ahead and take a look at the next one. Notice how it's a natural log, so we have to think about if we were to convert it to an exponential, what should our base be? E, good. Okay, so natural log is a base of E. Logs are powers, so this log answer of 3 is the power on that base of E, and the argument is the output, in this case, which would be x. All right, so I converted a log to an exponential. You could leave it like that because technically this is an exact solution. Some of you might feel a little bit more comfortable though typing it in, getting a decimal. So we can do second natural log. It'll bring up that e to a power command, and I can just type in 3 for the power. We'll get 20.086. All right, if you wanted to check your work, you can. I'm going to take this 20.086 and plug it in for this x. So I'll hit the natural log button, which is right next to 4. Type in 20.086, and if I hit enter, I'm hoping for something close to 3, which it is. Okay, a little off because we rounded, but still pretty good. Okay, so notice how we can convert to help us solve these log equations, or maybe we can convert to eventually help us solve exponential equations because we have this connection, aka conversion, between the two. All right, can we try the next one? Can we convert it? Are we starting to get into a routine, a groove? What's our base? 3 power, negative third, and that's going to equal the argument. All right, if I solve it, I see a negative power, so I can flip the base. 3 cubed is 27. Let's see. Maybe we'll get a decimal. I'm going to do 1 over 27, so 0.037. And from there, I'll go ahead and solve for x. So you can subtract 1, divide the 2, and negative 0.481. Do we want to check our work, or do we kind of trust our gut with this one? Want to trust it or check it? We'll check it just for practice. Okay, math, we'll go down to letter A. My base is 3. And for the argument, I'm going to do 2 times my x answer. And then I have to add 1. Okay, when I hit enter, I'm hoping I get something really close to -3. Which I do. And it's a little off, again, because we rounded our final decimal. Okay, you could have kept this a fraction and solved from there and have your answer as a fraction. That's okay as well. Okay, but however you want to represent it, it's fine. All right, how about the next one? Can we convert it? Our base is 25. Our power is x, and this equals 5 times the square root of 5. Okay, let's see how we can approach this one. I have the same base on the right-hand side, so maybe since I'm multiplying them together, I can combine their powers in some way. The power on my first 5 is 1. Okay, understood 1. What's the power on the square root of 5? I have a half. Okay, and if I'm multiplying the bases together, what can I do to the powers? Can we visit our properties from last unit? If you multiply the bases, what can you do to the powers? Add them. Okay, so 1 plus 1.5 would be 1.5, or 3/2. Do we have any kind of intuition to go from there? Any gut feeling? Yeah?
3 by 25 is 5 squared.
Okay, we can get a common base. And by rewriting 25 as 5 squared, you're creating another property. We have a power to a power, so we'll multiply those together. Now that we have the same base on both sides, we can just go ahead and set equal the powers, because we want those to be the same as well. The left side and the right side have to be equal. So if I take 1.5 divided by 2, that's going to give me 3/4. Okay, if you have $1.50 and cut it in half, you'll have 75 cents each. There we go. Let's check it. Okay, what's nice about this particular example compared to the other ones is notice how this logarithm was completely comprised of numbers. Did you notice that? Whereas the 3 previous ones had an x in them in some way. Do you see the difference? So since this logarithm is completely numbers, we can go ahead and type it in. Let's go ahead and check to see if this 3/4 was done correctly. All right, so my base is 25, and my argument, I need 5 times the square root of 5. And notice how you'll get 3/4. Okay, so I know if you have a calculator, you can go ahead and just type it in since it's all numbers and get your solution. But notice how we were able to do the same example without a calculator. It just involved using some properties of exponents, but we're good with those because we spent quite a bit of time with them on the last unit. Okay, let's try our next one. This logarithm is all numbers as well. Maybe we can think about this one. Can you think of what power you have to raise 2 to get 9? Can we think of it exactly? If not, can we think about it? What should be? It should be between. Yeah?
Between 3 and 4.
Between 3 and 4. Okay, so 2 cubed is 8. 2 to the 4th is 16. 9 is between 8 and 16. So this logarithm should be between 3 and 4. Since it's all numbers, let's go ahead and type it in. I know we're probably in the groove of converting, okay, which in some cases is absolutely necessary, but if it's all numbers, maybe we can use a calculator to our advantage. We tried to do it in our heads, but we couldn't think of it. We figured out what it should be between, so now we'll utilize the calculator to get it exactly. So we'll say 17 if we round it. Can we solve for x? We'll get 1.17. All right, so there's our solution. Let's think about this a different way. Let's say you were in the groove of converting these. If we did convert this logarithm, our base would be 2, our power would be x plus 2, and that should equal 9. And if we converted it, we probably should try to get a common base like we did in the previous example. Is there any way you can get 2 and 9 to have the same base? Probably not, because 3 would make sense for the base of 9. So if you cannot get a common base, realize that you would have to use your calculator anyway to help you find the intersection point, okay, by graphing both. And I would be willing to bet if you did an intersection point, you'd get the 1.17 like we did previously. Maybe you want to double check it just to be safe. Okay, but if you were into that groove of converting, you'd still be able to solve it, maybe not necessarily by hand, but we do have those techniques for exponentials like we did in the last unit, where you can find those intersection points on your calculator. All right, let's try our last one. This logarithm, unfortunately, is not all numbers, so we can't just type it in to get a value. It seems like in this case we have no choice but to convert it to help us solve. So can we think about what that would look like? What's my base if it's a natural log? E. What's my power in this example? I heard 5, and that's going to equal x plus 3. All right, so to solve for x, we could simply subtract over the 3, and you can leave it like this, e to the 5th minus 3. That's an exact solution. Some of you, though, might be more comfortable with decimals. So if you wanted to type it in, e to the 5th minus 3, we'll get 145.413. Okay, so I can't really tell you, like, this is the technique we always have to use when it comes to solving log equations, because it's just going to vary depending on what we have. Sometimes converting it is going to be a good bet. Sometimes using your calculator, if you can't figure something out, is going to have to be used. Maybe we're going to have to use some properties of exponents to help us out. It just depends on the type of function we have. Now, again, these are very basic, okay, just getting the idea of converting, but we're going to amp them up as the unit goes on. Okay, so, and we're going to talk about them. We'll take our time with them, but realize that this was just something basic. Okay? Tomorrow we're going to take a look at some properties of logs. Just like how we use some properties of exponents today, we're going to see what the properties of logs are like. And I'm hoping that we realize that since logs and exponentials are related to each other, their properties are related to each other as well. So if you're already familiar with the properties of exponents, which we did in the last unit, then these new properties we do tomorrow, I'm hoping, are going to be kind of second nature to us, because there is a connection between the two. Are we doing okay?
Yes.
Are we sure?
Yes.
Okay. We'll call it a day.